The best DRAMs for artificial intelligence. The choice of the DRAM depends on where the action is. Artificial intelligence, AI, involves intense computing and tons of data. The computing may be performed by CPUs, GPUs, or dedicated accelerators, and while the data travels through DRAM on its way to the processor, the best DRAM type for this purpose depends on the type of the system that is performing the training or inference. The memory challenge facing engineering teams today is how to keep up with the rapidly increasing computational requirement for AI. And synchronous DRAM plays a critical role. All that data needs to be processed, stored, and accessed, and any mismatch in those steps can impact overall system performance. We are setting all this compute power, said Frank Farrell, Product Marketing Group Director at Cadence. But how do you take advantage of it from a memory bandwidth standpoint? There is no simple answer, and no one-size-fits-all solution. Today there are 4 classes of synchronous DRAM as DRAM, each with its own targeted uses and trade-offs. 1. Double data rate DDR memory tends to accompany CPUs and compressed instruction set architecture, or CISC processor in particular. Programs may have complex branching and a wide variety of operations, and DDR is optimized for such computing. DDR is the most general purpose architecture, has latency, time to the first data, that beats all the other types except for HBM, with moderate bandwidth due to the 64-bit data bus, and double data rate aspect refers to the fact the data is clocked into and out of the memory on both rising and falling edges of the clock. This was not typical for prior memories and most logic, which clock only on one edge. 2. Low power DDR, LPDDR, is similar to DDR, but it includes a number of features that were gradually added over successive generations in order to reduce power while maintaining high performance. Its power-saving features include lower power voltage, a temperature-compensated refresh rate that allows less frequent flash when cold, deep and partial power down mode, partial array refresh options, right leveling, which compensate for skew between the data strobe and clock signals, command and address training to optimize signal time and integrity, lower I/O capacitance, a 6-bit single data rate SDR command and address bus on the later generations rather than a prior 10-bit DDR bus, 2 half-width buses rather than 1 full width, differential clocks, data copy and write X, write once or zeros, commands to reduce data transfer for those use cases, and a differential voltage and frequency scaling, DVFS. Later generation contain a more complex clock structure that has a quarter speed master clock learning constantly, from which multiple full-speed clocks are derived that run only when necessary. LPDDR is not built into dual inline memory modules, DIMMs. Instead, it is housed in BGA packages or grid array to be consoldered directly to the board. 3. Graphic DDR, GDDR, is a variant created to accompany GPUs for graphic processing. It has much higher bandwidth than a DDR for feeding large volumes of the graphics data to the processor, but it also has a higher latency than the DDR. GDDR is much better for bandwidth, but capacity is a problem, said Fellow. 4. High bandwidth memory, HBM, involves stacks of DRAM chips with very wide buses that can provide the very high bandwidth and a low latency necessary to keep memory access from being a bottleneck in data-intensive computing such as AI training, AI inference, and high-performance computing, HPC. The primary differences in these four DRAM types are access protocol, not the memory cells, where you are using GDDR, LPDDR, DDR, or HBM. It's basically all the same memory technology underneath the hood, not Fellow. You've still got the basic DRAM technology. It's about your accessing that DRAM. Those different access approaches can have a big impact on the performance and power consumption. Figure 1. Comparison of different SRAM families. Capacity is on a per die basis, not per stack for HBM. No single family excels at everything. DDR and LPDDR can have comparable throughput and capacity, with the cost being a major differentiator. Source: Brian Moyer, Semiconductor Engineering. So, king of the data center. The data center is HBM's undisputed territory. We believe HBM will remain primarily the domain of data centers for training and ultra-fast interface, said Lemteja Tadishetty, Principal Software Engineering at Expedia. But the price tag of the HBM likely keeps it in the cloud and away from cost-conscious edge devices. HBM consumed more energy and has a higher price, but so does everything else in the data center. While HBM is the most expensive and most power-consuming choice for local memory, and the cost power around the era compared to the cost and power of full reticle-sized die used in the training chips, observed Steve Roddy, Chief Marketing Officer at Codry. To use your real estate analogy, if you purchase a plot of land in the Beverly Hills for $25 million, you don't get screamed and saved on the build cost of the house. The same is true in the data center. Once you've committed to the expensive die and packaging, the HBM increment is inconsequential. The corollary to that is we have not seen any planned use of HBM outside the data center. Not even the high-end automotive market. Car companies building high-end SAE level for automated driver assistance systems. ADAS want silicon solutions that are air-cooled and cost less than 4 figures. They cannot accommodate 1000 watt modules that cost $10,000 or more. This cost consideration will focus those who can't afford HBM to make compromises. Hyperscalers typically have a deep enough pocket and enough resources that they can go for HBM, explained Brad Murdoch, product line director of memory interfaces and Synopsys. Second-tier players have to start making trade-offs as they don't necessarily have the volumes necessary to get the attention of the HBM vendors of the 3.5D assemblers to support an HBM solution. HBM is particularly important for training, which requires a higher bandwidth than inference. It's still used for data center inference, but LPDDR and GDDR are gaining traction there as well. HBM has become popular for nearly memory usage for training these models and Pharaoh. My guess is that GDDR and LPDDR are going to be the dominant memories in inference accelerator cards. Murdoch agreed, pointing to the more of a mix. Training requires more memory than inference, so one might desire a combination of HBM4 and LPDDR6, where the LPDDR6 is alone for the capacity ride. Unless you've already taken the step down from HBM4 to LPDDR6 for other reasons. Samsung is witnessing a similar trend. We are seeing a lot of mixed memory, said Calvin E., Senior Director of IP and Ecosystem Marketing at Samsung. It's not going with the DDR, LPDDR, GDDR, or HBM. We are starting to see mixes to save on power. Where do you mix DDR and LPDDR, or HBM and LPDDR? One emerging angle is custom HBM, where high-volume purchases can work with memory makers to swap the standard logic-based die at the bottom of the stack for a custom die with proprietary value-added functions or even optimized channels. Going to a custom HBM, where you can use some kind of a proprietary die-to-die protocol, will give you better bandwidth and better show line efficiency, noted E. While heat is a constant for all memories, it's critical for HBM because it's a stack, and if stack raises challenges for thermal dissipation, especially from dies in the middle of the stack. Multi-physics simulation are necessary, but those require more precise models. There are a number of challenges in representing the thermal behavior of such a 3D stack, said Roland Janke, head of design method department of Fraunhofer IIS Engineering of the Adaptive System Division. This obviously true for memory stack, but also if you have a stack including processor, memory, sensors, or whatever. And finally, where the geopolitics. Another consideration beyond availability and cost is politics. If I paint with a very big broad brush, it fail to say HBM is essentially off limits to China, noted Murdoch. So Chinese companies are using LPDDR5X for their AI designs of today and are moving to the LPDDR6 to their AI designs of tomorrow. CPU constant companion. DDR has a role in the data center, but it usually serves the CPUs, the coordinate operations. Accelerators, where GPUs or neural processing unit (NPUs) typically rely on HBM in the data center and/or LPDDR for higher bandwidth or low power, respectively. Figure 2. Memory employs with the CPUs versus GPUs. DDR accelerates general purpose sequential computing of the sort, and the CPU would typically execute, whereas HBM and LPDDR provide a higher bandwidth or lower power for the masses of data necessary for training and inference algorithms that involve high level of parallelism. GDDR also may appear there. Typically, servers in DDR go hand in hand, said Murdoch. Today, DDR5 RDIMMs are the gold standard, but some are moving toward DDR5 MRDIMMs, multiplexed RDDIMM, which can double bandwidth by ping-pong to RIRDIMMs, as they offer increased performance using DRAMs available today. The DDR5 MRDIMM comes at a premium both in terms of pricing and power consumption. But DDR isn't optimized for handling AI data patterns. DDR remains a reliable secondary storage method, said Expedita's Tashi Shetty. However, unless there is significant improvement in latency and performance, it cannot compete with the LPDDR in terms of efficiency and GDDR HBM in terms of low performance. That said, it's everywhere and it's cheaper. For volume inference optimized devices that aren't power constrained, DDR is the local memory of choice, said Radi. For any device that's line powered, home, office, factory, or comes with its own power plant, car. The speed and cost combo of DDR is an undefeated champion. Inference application running on NPU subsystems that smartly managing external memory are able to batch and prefetch DDR accesses to maximize performance while taking advantage of the enormous economics of the scale of the DDR availability. The new belle of the ball. Still, LPDDR is starting permit a wide range of systems, and if it doesn't displace an alternative, it might be added to the mix to lower power. For battery and power constrained devices, LPDDR offers a superior bandwidth versus power trade-off, said Radi. The massive volumes of LPDDR produced for phone market make it the cost-sensitive choice for the most emerging AI-centric consumers and portable devices. Others agree. LPDDR jack of all trades of memory, and in fact, master of some, said Moda. It owns both the mobile and automotive application spaces. One can even try to create a poor person's HBM with it. You can stack LPDDR to get a capacity, noted John A. Bill, Vice President of the Product Market for Memory Interface Chip at Lambus. LPDDR also is making its way into the data center as one way of reducing power, although it fails to offer everything hyperscalers want. The main drawback with LPDDR is its lack of RAS, reliability, availability, serviceability, RAS features, and it doesn't have the same degree of EGC, said Apple. Or there's this chip kill notion, where you can recover from a DRAM chip dying. LPDDR wasn't designed for that levels of kind of RAS capability. And even though DDR tends to accompany CPUs, LPDDR has toe in door. NVIDIA introduced their Grace ARM-based processor, and they chose to tie it to the LPDDR memory. Ever added, LPDDR also may replace DDR in edge systems where performance matters. Many edge devices don't have memory, and those that do often need very little, so they tend to look for whatever is cheapest, said Murdoch. Though that actually requires some levels of performance from the memory, use LPDDR to reach power and performance profile. Always bridesmaid. The one family less often seen in AI system is GDDR, which has characteristics that should appeal to AI systems, except that it tends to be second best across key parameters. Its throughput is higher than that of LPDDR, but lower than that of HBM. It costs less than HBM or LPDDR, but not less than DDR. There is no obvious parameters that would mandate GDDR for some classes of systems. As a result, it's often passed over for AI. GDDR seems to be anti-Goldilocks for AI applications, Roddy said. It's always just wrong. GDDR is too expensive for inference-oriented consumer devices, and well-designed NPUs with offline compilation can intelligently prefetch weights and activations such that the faster random access speed of GDDR is never needed. And in the data center, the low speed advantage of HBM has displaced GDDR. However, it's promising for graphic-related generative algorithms as long as its limited capacity isn't a barrier. It's primarily used for graphics and a certain aspect of generative AI, said Tadi Shetty. As we observe an increasing trend in image and video generation models, some demand might be shifted to GDDR. But to be clear, we have not seen OEMs doing this yet. 4 roadmaps. All of the DRAM standards originate in JEDEC, but each type has its own committee. DDR is owned by the JC 42.3 subcommittee, typically JEDEC nomenclature, with the JC 42 of covering the all solid-state memory, JC42.1, standardizing GDDR, JC42.2, handling HBM, and JC42.6, working at LPDDR. All four continue to push their DRAMs, but the LPDDR and the HBM versions are getting more attention. LPDDR5X is rapidly available, regionally affordable, and can fit the power and performance needs for many applications, said Mora. We are already seeing demand for LPDDR6 design start to give the performance boost it brings compared to the LPDDR5X. While the specific changes in the LPDDR6 aren't yet public, they are largely expected to be affect the clock speeds, banking, bandwidth, and burst accesses. In addition, it's getting built-in error correction called ECC, which is a testament to the delicate nature of the cells and signals at these high speeds. It's expected to be available by the end of this year. HBM4 are the next eagerly awaited version of the high bandwidth memory. It doubles bandwidth, chat counter, and the data bus width compared with HBM3. It's expected to ship in 2026. HBM3E is what is readily available today, but the HBM4 JEDEC standards have just been published, so design start will swiftly be moving to the HBM4 for the increased performance it will offer, said Amada. A dynamic environment. Even as memory speed improves their relative power drops, processors are undergoing similar development. Ideally, processors and memories move forward together, with neither one being the bottleneck, but they are developed separately, so there will always be some leapfrogging going forward. Although dedicated MPUs have had a hard time gaining traction in high volumes, some of the promise such lower power execution, if they catch on, and they will put yet more pressure on memory used in power-constrained systems. Likewise, a data center processors achieve higher performance, HBM will need to keep up. And simply picking the right memory isn't enough. Ensuring the high-quality access signal is critical to operating at high speeds. Those channels are really the most important thing from a system performance standpoint, and we got to look at the signal integrity, said Kenneth Farrow. If I'm a system designer, I should be able to take a GDDR6 DRAM from one vendor and drop in a GDDR6 from another vendor. But one may run at a 16 GB per sec, another DRAM might have an 18 GB per sec version. You can drop that one in and it work, but you can't that channel handle 18 GB per sec. Although the clear trends are in play, system designers still need to do their homework to identify the most appropriate specific memory for a given system, and to ensure that the system can keep up. Okay, today I read this article, The Best DRAMs for Artificial Intelligence. Thank you for your time. See you next time.